Okay, so we are looking at planning, and in the last class we had looked at this language called PDDL. Very briefly we had talked about this planning domain description language, and we are looking only at the simplest version, which you can say is version 1.0, which is equal to the strips domain. In the simplest version of the language, actions are instantaneous, the world is deterministic, the world is completely observable, the goals are simple in a sense that only the goal state is looked at and nothing else, and the agent is the only one who is changing the world. But we took the first steps towards reasoning. So, when we start talking about a language like this planning domain description language, we are talking about representation, how to represent domains, how to represent actions. So, typically if you look at a PDDL document, you would say they would start off by defining domain. So, the domain that we are looking at is the blocks world domain. So, you would say domain name is blocks world, the predicates are on table, holding, and all those predicates, and some of the actions we saw. So, let me write a couple of actions. Stack x on y, and the preconditions are the set of predicates which must hold for that action to be applicable, and the precondition for stack was on x y, then clear y and arm empty. So, A stands for arm empty, we will use this short form. So, if x is on y, so of course, x and y are variables here in the operators, but when we actually talk about a domain, they will get bound to constants which stand for specific blocks like A and B and C and so on. So, if x is on y and y is sorry, so somebody should have pointed this out. You should be holding x. If you are holding x and y is clear, then you can stack x on y, and the effects positive are on x y and arm empty, and the effects negative are holding x and clear y. There is one more positive effect, which is you can add as clear x. This is not precisely the syntax which PDDL uses. PDDL uses a more Lisp like syntax. So, everything is in brackets, and you say effects, then positive effects, then negative effects are actually a continuation of positive effects with a not prefix, but we will use this simpler notation here essentially. So, basically operators or actions are represented by these three kinds of things. One is a set of preconditions holding x, clear y, for example, and then the effects. So, what are effects? Effects are what are the changes that this operator will make in the world if that operator is executed. So, what we are saying here is that stack x y is possible when you are holding x and y is clear, and if you execute stack x y, then x will be on y, the arm will be empty because you would have dropped x in some sense, and x would be clear, and this will no longer be true that you are holding x and clear y. Similarly, we had defined unstack of x y, which is the inverse of this. So, the preconditions are on x y arm empty and clear x. So, if x is on y and arm is empty, which means the robot arm is not holding anything. Remember, we are talking about a one arm robot which is moving blocks around, and clear x, which means nothing is on top of x. Then the effects positive are holding. So, you can see here there is a kind of a association with that clear y, and the effects negative are these things on x, y, arm empty and clear x. So, in this version I have added clear x both to effects and here and there. So, if you add it here, then you must add it in this also. We have seen that earlier. Okay. So, as I said, this is the simplest version of PDDL or PDDL 1.0, in which actions are instantaneous and the other effects that we talked about. So, just before we move on to the planning operators, let me illustrate a couple of richer language constructs essentially. So, one thing which a richer language would apply is called conditional effects. So, conditional effects are effects which come into force only if certain conditions are true essentially. So, as an example of conditional effects, let us say that you have a domain in which you are talking about moving objects around and so on and so forth, and you have trucks and you have this kind of thing, and you want to move, let us say, one table from location A to location B, and you define a move truck action which says the truck goes from location, let us say, x to location y, and the conditional effects of that are that if there is any object in that truck, then that object also moves from location x to y essentially. Or if you look up the web, you will see something like a briefcase domain. So, if a briefcase goes from location x to location y, so let us say you have a bag that you carry from department to hostel, then if there is a book, a conditional effect will say if z is in briefcase, then z goes to location y. So, I am just writing it in sort of semi English, but the basic idea is that the act of moving a briefcase from location x to y has a conditional effect with in the sense that whatever is inside the briefcase will also get moved to the target location essentially. Now, of course, in this there is no such thing, the effects are deterministic and every action has very clearly well defined effects essentially, but that is a richer language. Another feature which richer languages have are derivative actions, which are being explored quite a lot nowadays. So, as we said in the last class, strips actions or PDDL1 actions have no concept of time involved at all, and that is because actions are instantaneous. So, if you are picking up an object or putting down an object or stacking an object or unstacking an object, we just assume that it happens instantaneously, and then once action happens, it is the effects are seen immediately essentially. But in the real world, of course, actions are not instantaneous, if you go from here to the hostel, it will take a certain amount of time to go from here to the hostel. So, that must be taken into account. So, durative actions are represented by durations or intervals so, this is the start of the action and this is the end of the action. So, for example, we consider this action of going from here to the hostel, then the action starts at a certain time t and it has a certain duration. So, there is certain amount of time t that is this action takes. Now, this time t could be constant or it could be a variable. For example, a move action in the real world, you go from here to the hostel, it may take you 10 minutes, you go from here to the department, it may take you 5 minutes, if you go from here to the gate, it may take you 15 minutes. So, the duration could be dynamic in that sense essentially. And so, this is the start of the action, this is the end of it. So, the action is defined over a duration and such planning domains are called durative, such actions are called durative actions. And what you have is that you have start conditions, or let us use the term preconditions, that is what we are using, and then start effects, and you have end conditions and you have end effects. So, what do we mean by this? That let us say that you want to go from here to a lab in the department and we have defined an action for that. So, the start precondition is that you should be here and maybe you have a bicycle or something or whatever other preconditions that you have there. What are the start effects? The start effects are the effects which come into play as soon as the action begins. So, the moment you start going towards the lab, you are no longer here essentially. So, that is a start negative effect essentially. What are the end effects? End may have preconditions. So, preconditions could be, for example, that the lab is open, that if the lab is open at this point of time, then the action will execute correctly, and the end effects could be that you could be inside the lab or something like that. And then we have overall conditions which are predicates which must be throughout the action. So, supposing you are cycling from here to some place, then the overall condition could be said that at all points your cycle has enough air. So, if the condition fails any time, then the action will no longer work. Now, as you can imagine, once you start talking about durative actions, then things become much more complicated. You have to talk about start effects, start conditions, end effects, end conditions, overall effects, overall conditions and so on and so forth. So, reasoning becomes much more complicated and you can imagine that one action may be like this, another action may happen like this, and then there are different kinds of relations between these intervals that you have to explore, and there is a well defined study about it which is called Allen's interval algebra, which basically looks at all the relations between which two time intervals can have or two intervals can have, they do not have to be time. So, this is for example, saying that the second interval begins before the first interval ends, and you can imagine that there are many different possibilities, they can happen simultaneously, the second one can start immediately after the first one, or the second one can be contained totally in the first one, or the second one can totally contain the first one. So, there are about 13 such intervals, and then there is an algebra which talks about reasoning with those intervals. We will not get into this here. The third thing that is often introduced is like metric values. So, these are numerical values which can take different values, and to take to illustrate an example here, it could be that instead of a bicycle, let us say you are using a motorcycle, then one of the things that you will need, one of the conditions that you will need is that at all points you must have some certain amount of petrol essentially. So, this metric values would keep track of the amount of petrol that you have in your motorcycle, and it could say something like if you have x amount of petrol at the start, then at the end of the action you will have x minus some k amount of petrol. So, that is a end effect that is there of the action, and that introduces a third dimension, which is that of continuous numerical values essentially. But we will in this course not look at these richer domains and focus more on the basic planning, which is done using the strips PDDL kind of a domain essentially. Okay. So, we had defined some things. We had said that an action A is applicable if, does anyone remember the preconditions of A? So, we will use this as a predicate. This stands for preconditions of A. So, which basically stands this set here is a subset of S. So, we should say applicable in state S. So, with this planning, as you will notice, we are sort of making a gradual transition into representation. So far we did things like search, but did not bother about representation. Now, we are talking about how to represent the domain, how to represent actions, and also we are keeping the reasoning part in mind, and the reasoning part is, at least to start with, will be the same kind of reasoning, which is searching for solutions essentially. So, because we have these explicit representations, we can talk about this kind of conditions. So, an action A is applicable in state S if the preconditions of A are a subset of S essentially. Likewise, we say a goal. So, when we say goal G, we essentially mean a set of predicates that we want to be true. So, for example, today we will look at an example where the goal is the following: on A B and on B D, let us say, which stands for the fact that A is on B and B is on D in the blocks world domain. So, this thing is the goal essentially, and this comma is to be interpreted as an and, which means that both the things must be true. A must be on B and B must be on D essentially. So, a goal is basically a partial description of a state that you want to be in, or the desired state essentially. So, we say that a goal G set, or let us say a state S satisfies a goal G. Remember, both of these are sets of predicates. A state is, for example, what is true in the world on A B, on B C, whatever, and likewise goal is what you want to be true in the world essentially. So, we use the word goal as satisfies, a state satisfies a goal G if in the representation that we have used G is a subset of S. So, you can see that this can be used to define the goal test function, that have we reached the goal or not. We are working with simple goals here, and we want to see whether we have reached a state which is a goal or not, and this can be used to test for that essentially. When an action A is applicable, we can define a function called progress let us say in a state S using an action A, and what this progress does is that it takes a state S and applies the action A and gives you a new state S prime, where S prime, as we saw in the last class, is S minus the negative effects of A union the positive effects of A. So, we have a progress function which allows you to move from one state to a next state essentially. So, we have basically the machinery for doing state space search here. We can test whether an action is applicable in a state or not by using this applicability test. We can progress from the state to the next state. So, in effect we have done the move gen function by if we just select all the actions which are applicable in the state, we have the move gen function, and then we have the goal test function here which says that you can test whether it is a goal or not essentially. So, forward state space search essentially does the kind of search that we have been talking about. So, let me give you a okay. So, a planning problem is defined by a start state as before, a goal. So, start S let us call it, goal G and a set of actions essentially. So, obviously, we have defined the domain using a language, and having defined the domain in the we have defined a set of actions that are possible in the domain, and a specific problem is when you have defined the start state S, a goal set G and the set of actions that are available to you defined which can be used to go from start to goal essentially. So, let us assume that we have some simple domain. So, we want that A, B and D. So, let us say our given start state is the following: A is on B. So, let us say this is on the table, and let us say C is on D, and then E is on the table, F is on the table, so some arbitrary start state I have given. So, let us say this is a start state, and that is a goal state that we want to achieve, which is that A should be on B and B should be on D essentially. So, again let me repeat that the goal is a description and the description may be true in many states. As you can imagine, if you just have this A on B on D, then the rest of the blocks can be arranged in any way, and as long as those two predicates on A B and on B D are there in a state, that state is a goal state. That is what we have said here, that a state S satisfies a goal G if G is a subset of S. Now, we want to do this planning, and we start with forward state space search, because that is what we are familiar with. So, how would forward state space search progress is exactly like the state space search that we have been talking about so far, that given this start state S, you can apply many actions, and so instead of writing the actions, let me just depict the actions by saying, by using these arrows. So, this arrow says that I am unstacking A from B, that is one action I can apply. I can unstack C from D, I can unstack F from E, I can unstack I from H, this I can pick up. If you remember, there were 4 actions we talked about: stack, unstack and pick up and put down, and the only difference between pick up and unstack is that unstack happens from another block and pick up happens from the table. So, just to illustrate how to use different actions, and this one. So, the move gen function in this particular state would generate these actions 1, 2, 3, 4, 5, 6, 7 actions, and your search algorithm will have to pick one of them essentially. Let us say it picks this action for some reason. Now, what is the situation? The situation is that this robot is holding this block k. Let us say if it picks this action, it is now holding this block k, everything else is a change. So, how do we define this new state? We define it by doing this progress action, which says that if I am doing this unstack kj action, I must apply this, I must remove the negative effects of A. The negative effects of unstack are that x was on y, in this case x is k and y is j. So, kj is no longer true, on kj is no longer true, arm empty is no longer true, because you are holding k, and clear x, which is this k, is no longer true. And then I must add the positive effects of this action A. The positive effects of the action A are that you are holding it and y is clear. So, this effect would be represented by the fact that you are holding k, and because you have lifted k away from this j will become clear. So, clear j will be added to the state. So, that is a progress action that you have to implement to get this new state k. Now, you can see that having done this action, these actions are still applicable. Sorry, actually they are not, but they would become applicable the moment the arm becomes empty. At this moment, this arm is not empty, arm is holding k. So, the only action you can do with this one arm robo, unfortunately, is to put k somewhere, either put it on the table or put it on one of the blocks. Now, this we can illustrate by saying that from here the actions are, you either put it on this, or you either put it on this, or you either put it on this, and so on and so forth. So, I will not draw the state space here, it is too difficult to draw, but you get the basic idea that you move from state to state, and whichever state you are looking at, you apply the move gen function, which is looking for all the actions which are applicable, pick one of them and move forward essentially. So, this representation mechanism allows us to do the old search that we were doing, which was we did not give a name to it. We have not yet given a name to this, we have only said forward state space search, because we have not talked about what the strategy is. Now, you could do depth first search, or you could do breadth first search, or you could even do DFID or something like that. You could do anything that we were doing here essentially. So, what is the difficulty with this? What is the drawback of forward state space search? If you look at this given start state and that given goal state, can you observe what this is doing wrong? And when you make this observation, you must keep in mind that we are not solving only the blocks world problem, we are writing this as a generic algorithm of forward state space search, in which you can plug in the domain with all its set of actions and operators and all the predicates. It is not goal driven essentially, and in fact, you look at the, I have purposely drawn this like this, because those 3 blocks A, B and D that you want in the goal to be true are here in the left hand side, and this right hand side is actually we should not care. Now, of course, the real world is like that. If you are, let us say, planning for yourself what to do next, then if you were to simply try to describe what is true at this moment in IIT, you would have hundreds and thousands of statements. Okay. You know, something who is there in the office, who is there in the lab, who is there in the canteen, what is happening, and you know, this class is going on there, this class is going on, hundreds and thousands of statements you would have, and then hundreds of thousands of actions would be possible essentially. When we look at this particular problem, we can see that there is no point in picking up f or I or k or L or m, because they are not going to help us achieve the goal, whereas something should be done on this part essentially. So, the problem with forward state space search, and this arises from the fact that the state description can be large, the number of applications can be large, is that there is a large branching factor. The number of actions which are applicable in any given state is just too many to be considered by a brute force approach, and that is true in any real world situation as well essentially. how do we address this problem? One approach is heuristic search, and that is something we will again not explore in this course, because we do not have enough time, and you are most welcome to come for the planning course if you are interested. And when we talk of heuristic search here, we are now talking in a domain independent fashion. Earlier we said, okay, for this 8 puzzle, this is the heuristic you can use, or for blocks world, this is the heuristic you can use, the number of blocks which are in the correct place and that kind of stuff. But we do not want to define heuristics in a domain dependent fashion. We are interested in talking about domain independent fashions, and the idea of domain independent heuristics is to solve simpler problems essentially, and the approach that we use in planning is to solve the what we call as the relaxed So, one approach is to solve the relaxed planning problem, and what do I mean by that? I mean that if I am in a start state S and I have all these possible moves from these states, let us call them S1, S2, S3, S4, S5, then I solve a relaxed planning problem going from this S1 to goal and S2 to goal and S3 to goal and S4 to goal and S5 to goal. Look at the solution produced by this relaxed, or as the solution is called the relaxed plan. Look at the relaxed plan and see which is the cheapest relaxed plan, maybe in terms of number of moves. So, if S2 is giving me the cheapest relaxed plan, then I will say, okay, I am going to make this move from S1 to S2. Exactly like in the heuristic search that we said earlier, we said that we will apply the heuristic function to all these things and choose the one which seems to be closest to the goal, except that here we are literally applying a problem solving strategy to solve from each of these positions to go to the goal and seeing which one seems to be closer to the goal. Now, the first question to arise is that you would ask is that computing the heuristic function should not be as expensive as solving the original brute force problem, because if that is the case, then what is the advantage the brute heuristic function is giving you. In the heuristic functions that we had seen so far, the domain dependent heuristic functions, we had said that it is a static function, you only look at a state and do a computation of a value. So, for example, you would do Euclidean distance, or as we said, the number of blocks and so on. So, they were cheap. In this case, we frame the relaxed problem in such a way that it is a easy problem to solve, which means computationally easy to solve, and when we say computationally easy, we mean polynomial time. So, if each of these states can be solved, can be posed as a relaxed planning problem, and it can be solved in polynomial time, then we will just have k times that polynomial time, and we will be able to decide on which one to use here. So, remember we had said that even in this simple domain, planning is hard. In fact, it is p space complete, which means it requires polynomial space and exponential time. And here we are trying to say that we will solve a simpler problem to try to estimate which of them is closer to the goal. And notice that this is being done in a domain independent fashion. How do we do this? The relaxed planning problem is basically says ignore the negative effects. Ignore negative effects of actions, and those are called relaxed actions. So, I just ignore this part essentially, and then you can see that if you try to visualize this becomes a monotonic situation. You keep adding new predicates to the start state, you are not deleting any predicates. The complexity of planning comes because you are deleting things, that you pick up k from j, k is no longer on j essentially. But if I am leaving on kj in the relaxed plan, then I am monotonically increasing the set of predicates, and at some point I will get those two predicates inside my set, and then I will say I have solved the relaxed planning problem. So, it turns out, and you should take my word for it, that solving relaxed planning problems when the effects, negative effects are ignored, is polynomial time essentially, and heuristic search essentially uses that approach. Okay. There are one or two other ways to compute heuristics, but we will not go into that. What we will do instead is to focus on doing what we call as backwards search. We have already got some exposure to backward reasoning. We said that AO star, for example, and or graphs are goal trees that you work from goal backwards, but there the representation was tailored to backward reasoning, that we said that this is how you decompose a given goal into sub goals, and then that sub goals into more sub goals, and eventually you have trivial sub goals to solve. Here we are not changing the representation, but we want to do backward reasoning. So, we need a few things now. Again we have to, so this machinery will no longer be applicable. We talk about something called relevant actions. So, we say an action A is relevant for a goal G. This is in some sense analogous to applicable actions. In forward state space search, actions are applicable in a given state. In backward search, we will use the term state space search here again. Actions are applicable to goal descriptions, and we say that an action A is relevant for goal G if the following is true. Let me write it here. The effects plus of A and G is not equal to phi. That an action has a effect which is required in the goal to be true, which means, so what you are simply saying is that the intersection of the positive effects of the action and the goal must not be empty, it must produce something which is relevant for the goal. Then we say action A is relevant, but there is another thing you want, which is that effects minus of A goal must be equal to phi, that it must not produce any negative effect which you want in the goal to be true. Remember what that the goal is a set of predicates that you want to be true, and you are looking for actions which will achieve the goal essentially. So, we say that an action A is relevant to a goal if the positive effects of A has something for the goal, which means the intersection with goal is not empty, and the negative effects of A is empty essentially. So, we have now two predicates in our goal, and you can see that two actions are relevant essentially. Can you tell me what are those two actions? So, I am moving from goal to sub goal now. I am saying that if I want this to be achieved and if this is my last action, then I will achieve it, but only I am only using this definition of relevancy essentially. I am not doing any deep reasoning here, I am just applying this test to see what actions are relevant. Anyone wants to venture a guess, hazard a guess?
A, B.
Stack A on B, and one more is stack B on D. Now, you can see the principal advantage that backward state space search gives us over forward state space search is in the branching factor, because backward state space search is focused on the goal, it is only looking at actions which will achieve the goal, and in this example you can see the branching factor is small, we have only two actions that we can consider, and here there were many actions that we were considering. So, that is the main advantage of doing backward reasoning or goal directed reasoning. Then we have to talk about regression. So, regress goal G with action A, which means how do you define the sub goal? So, you get G prime as G minus effects of A. because action A is producing those effects, we don't want them to be true in the previous state or the previous goal description. Union, anyone? Preconditions of A, because that actions must be true in must be applicable in the previous goal state. So, this is called regression, and if you want to regress now over this, you can see that I must remove the effects of stack A B, which is on A B, but I would be left with on B D, and now I need the preconditions of the stack action, which is holding B and clear D. Correct. In a similar fashion, for this I can regress to on A B is here, holding B, clear D. If I am going to stack B on D, I must be holding B and D must be clear. So, that is why I have added it to the this thing. So, I am moving backward from the goal to sub goals in some sense, and this is a process by which I will search backwards. The main advantage that I am looking for is lower branching factor, because I am only looking at actions which are needed for my goal to be achieved, but there is a problem here. Everywhere there is a problem, right. What is the problem here? So, look at this second action. So, if you visualize what you are doing, okay, you have this A on B and B on D, and you are saying that my last action would be to stack B on D. So, just if you try to imagine that, you will see that it is practically impossible, because you cannot be holding B when A is on B. So, if you look at these two, then they are inconsistent, cannot be true at the same time. Moreover, if I were to regress from here, I could say stack, I could take any goal, right. I could pick an action to achieve this goal, which is to stack B on D. I could pick an action to achieve this goal, which will be unstack B from somewhere or pick up B from the table, and I could choose an action to achieve this goal, and that action would be to unstack something from D essentially. Of course, unless D is already true, but I can choose the first one. For example, I can say stack B on D, and when I regress to this, I get those holding B, clear D, and then the preconditions of this, which are holding be holding A, clear, and this should be clear B. So, I will have holding A and clear B's, and this holding B and clear D come because of the stack BD action. Again, you can see that this is an impossible state. It is not a this is not possibly a state, whereas this is a state. You can agree, because B is on D and you are holding A and you are about to stack A onto B. That is perfectly feasible. In fact, it will be part of the plan that you are looking at. This is not feasible. This says you are holding B and you are holding A at the same time, and then you have this one armed robot which is trying to do this. So, backward state space search has this advantage that we get a low branching factor because it is goal directed, but it has a disadvantage that what we get are not states essentially, may not be states. Now, this progress action is sound, and by sound I mean it is closed over the state space in some sense, is that when you apply a progress action to a state, what you get is a state. So, in that sense it is closed over the state space, the regress action is not sound. When you apply a regress action to a goal, you get a goal description which may not necessarily be a state essentially, which may not be possible part of a state. So, for example, this cannot be part of a state. How can you be having on A B and also holding B essentially? That is not allowed in the rules of the game that we have defined. We have a one arm oboe which should be holding B, and then so because it is holding B, nothing can be on top of B. So, this is not possible. So, how do we get around this problem? So, this is not sound. So, there are two things that you can do basically is okay, when do we stop this backward state space search? When we reach a start state, what do you mean by that? What is the test that you will use?
Preconditions of the actions applicable.
This is a subset of search.
You terminate this when that G whatever prime 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 that we have is part of the start state. Remember that you are regressing from one goal to another sub goal to another sub goal to another sub. If at some points you have a set of predicates which are true in the start state, that means you do not have to do any more actions. You are already home, so to speak essentially. So, this is a condition that you will use. So, you should verify that it is possible for me to construct a plan like this using backward state space search, but this is not a valid plan. So, I can do a check for a valid plan. How do I do that? So, what is a check for valid plan? A check for valid plan takes as arguments a plan pi, basically it takes a problem description and a problem description and a plan, and the problem description is a start state and a goal description and a set of actions. So, with this input you can write a small routine which will begin with the start state, and I will not write the details here since we are running out of time. We will begin with the start state and keep progressing with the actions. What is actions? This pi is A1, A2, AK. So, the plan is made up of k actions. You begin with the start state, apply the first action, and we have seen that this progress is a sound mechanism. You will get a new state, apply the second action, to that you apply the third action, and till the end you keep applying the actions, and then you see whether the state that you reach is a goal state or not. And you will see that if you construct a plan like this test will fail, that it will say that this is not a plan. Why? Because for example, this action will not be applicable at all, because you will never reach a state where you are holding both these things together. So, you can do that check essentially. Another thing we can do is to check for consistency. And prune because the start state may have hundreds of facts. So, for example, here we have facts about f and e and h and g and k and j, they will never be generated in the backward phase from there. We will never talk about k and j. So, it will never figure in the goal description. See, what will happen is that you will say I want to stack A on B and I want to stack B on D. So, first I want to stack B on D and then I want to stack A on B. To stack B on D, I have to first pick up B. To pick up B, I have to remove A. So, it will remove A, pick it on the table, then pick up pick up C and remove it on the table, so that D becomes clear. Then it will pick up E and stack on D, then it will pick up A and stack it onto the floor. Those will never come. So, those are in the start state. So, that is why this subset is necessary. This check for consistency is basically, just a moment, this check for consistency is basically trying to prune states. It is saying remove this state, do not go backward from here, or remove this state, do not go backward from here, instead go along this direction. Now, as you can see, in the actual plan this will be the last action stacking A on B, that will necessarily be the last action. The previous action must be to make this true, or to make the previous action must be, or maybe it is to make clear B true. Once B is made clear and then you holding A, for that the action will be pick up A. If you look at this carefully, you have to first put A on the table and then you will have to pick up A from the table. So, the third last action would be pick up A. So, there are paths which will yield the plan, there are paths which can be pruned, and then even if you do not have good pruning, you have this final check that after you think you have solved the problem, just see whether what you have produced is a valid plan or not. If it is a valid plan, then accept the solution, otherwise continue searching essentially. And the good thing about this consistency check is that it does not have to be perfect. If it is perfect, it will prune this state. If it is not perfect, it will not prune it. You may produce a series of actions and you will find it is not a plan, and then you will come back and try again. So, even if you have an imperfect consistency check, it will still work essentially. So, in the next class, we will try, as we keep doing all this time, to look at an approach which will combine the good features of backward search and forward search. The good feature of forward search is that it is sound, that whatever sequence of actions it produces are valid plans, because the applicability test is sound. The good feature about backward state space search is that the branching factor is low, but the bad point is that it produces these spurious states. This is not a state at all, it is a spurious state, and we have to do unnecessary extra work to remove those states essentially. So, we will try and see an algorithm which will search in a backward fashion like this and construct a plan in a forward fashion like that essentially. What this is doing is searching in the backward fashion and constructing a plan also from the last action backwards. This is the last action, this is the second last action, and so on, which as you have seen is not a sound process. This one is constructing sound plans, but it is doing too much search. We want to combine the two, and we will do that in the next class. Okay, so we will stop here.